So we have seen that you can use derivatives to find the instantaneous rate of change. When you have an equation that relates two different things, you can use derivatives to find the instantaneous rate of change of one variable with respect to another. So that's what we're going to look at today. We've done lots of examples where we found the instantaneous rate of change of velocity or um, position function by using derivatives. So now we'll look at some other applications. This first one says or asks us to find the rate of change of the volume of a cube when each side length is 12 centimeters. So what this is meaning is that the volume is changing its dimensions. Okay, it could be getting larger, so it could be starting with an edge length that's less than 12 and getting larger, or it could start with a length of each edge length greater than 12 and getting smaller. Doesn't matter. Okay, we'll find out at the end whether it's getting larger or smaller by whether the answer we get is positive or negative. But we need to find the instantaneous rate of change of volume of a cube when each side length is 12 centimeters. So to do this, you need the formula for the volume of a cube. So if we say that, let's say L is the length of each side, and a cube is a three-dimensional shape where the length, width, and height are all the same. That's what a cube is. So the volume of this cube would be length times length times length. It's length times width times height, but because it's a cube, that means all those dimensions are the same. So volume will be L cubed. So we need this formula as a starting point. And on the test that you guys will be writing next week probably, any of these formulas that you need, you'll be given. So you don't have to know all these formulas. So there's an expression that relates the volume to the length of each edge of the cube. And the instantaneous rate of change of volume with respect to L would be dV by dL. And that would equal 3L squared. You're taking the derivative. The derivative of volume with respect to length of each edge is dV by dL. And then we differentiate L cubed and we get 3L squared. So now we can find the instantaneous rate of change with respect to velocity. So the derivative dV by dL at 12 centimeters would be 3 times 12 centimeters all squared. 12 is 144, so this will be 3 times 144 centimeters squared, which is going to give us a positive value, which means that the cube started with a smaller edge length than 12 and it was getting larger, and this is the instantaneous rate of change, 432. And it would actually be centimeters squared per centimeter of edge length. And I guess it actually, because it's the rate of change of volume, it would be centimeters cubed, because volume is measured in units cubed. So the volume is increasing at an instantaneous rate of 432 centimeters cubed per centimeter of edge length. That's what that means. Okay? So number 2 says find the rate of change of the area of a circle with respect to its radius r when the radius is 2.3 meters. So again, this means that the circle is changing in size. Once again, we will know at the final answer whether it's a positive rate of change, meaning it's getting larger, or a negative rate of change, meaning it's getting smaller, but we need to find the rate of change of the area of a circle with respect to its radius. So we need to have a formula that relates area to radius, which would be the area formula. If we use it in function notation, A at R, area as a function of R would be pi R squared. That's the formula for area of a circle. 2 pi R is circumference. So in this case here, you have to realize that pi is a constant, right? It's an irrational number, but it's a constant. So when you differentiate this, so we'll say A prime R, it'll just be 2 pi R, which is the formula for circumference of a circle. But that's not why you get 2 pi R. It has nothing to do with circumference. It just happens to be the same formula. Okay? So there's our expression for the derivative, which can be used to find the instantaneous rate of change. And in this case here, we want to find out what that value is when R equals 2.3 meters. So it'll be 2 times pi times 2.3, 2 pi times 2.3. And so it's an irrational number. So you can write it like this as an approximate value, approximately 14.45. But we can also write it as an exact value. Just multiply the 2 and the 2.3 together, you'll get 4.6 pi. And because it's area that's changing with respect to radius in meters, it'll be 4.6 pi meters squared per meter. So by writing it like this, we have expressed it as an exact value, not a decimal that would need to be rounded. But the area is changing with respect to the radius. So the area is measured in meters squared, the radius in meters. A spherical balloon is being inflated. Find the rate of change of volume with respect to radius when the radius is 10 centimeters. So we need to have an equation that relates volume with respect to the radius. And the volume of a sphere, which is a ball, is 4/3 pi R cubed. Again, if you needed this on the test, you'd be given these formula. But because we want to find the rate of change of volume with respect to radius, we have to have an equation that relates volume to radius. And the formula for volume of a sphere does that. So now the instantaneous rate of change of volume with respect to radius will be the derivative. And when you multiply the power 3 and it comes in front as a coefficient, the 3's are going to cancel and you'll have 4 pi R squared, which is actually the formula for surface area of a sphere, 4 pi R squared. Again, that's just the way it worked out. So now we want to find the instantaneous rate of change of volume with respect to radius when the radius is 10 centimeters. So it'll be 4 pi times 10 centimeters all squared. 10 squared is 100 times the 4 would be 400 pi. And this is the rate of change of volume, which would be measured in centimeters cubed per centimeter change in radius. So again, by writing it like this, we've expressed it as an exact value. I said that twice already this morning. Yeah, I know. You got a tough life, Brighton. I get it. I know. I don't know how you do it some days. Okay. The mass of x meters of rod is given by F at x equals x squared kilograms. The linear density P of that section of rod is given by P equals mass over length, and the average density by, and again, that's just that slope formula that we've seen before, to find the average between 2 points along a graph. Determine the average density of the part of the rod between 2 and 2.3. and then determine the linear density. And the linear density is the instantaneous rate of change of mass with respect to x. So we're going to use that formula above, f at x equals x squared, for that part. Okay? So before that, we need to first find the average density, and that would be done using basically that slope formula. That's what f at x2 minus f at x1 over x2 minus x1 is. That is the slope formula. F at x2 is the same as y2, and f at x1 is the same as y1. So part A, essentially we're finding the slope of this. And so it's f at 2.3 minus f at 2 all over 2.3 minus 2. So if we use the formula above, f at x equals x squared. So it'll be 2.3 squared minus 2 squared all over, that'll be 0.3. 2.3 squared minus 2 squared is 1.29, which is then divided by our 0.3, which gives us 4.3. And so this is the average. So the mass of the rod is in kilograms per meter of rod length. So it'll be 4.3 kilograms per meter of rod length. And then part B says find the instantaneous rate of change, which will be the derivative, f prime x. F at x equals x squared, so f prime x will be 2x. And so now we want to find f prime at 2, which will be 2 times 2, or 4 kilograms per meter. So if you think back to when we first started talking about finding the slope of the tangent, and so we used secant points that were getting closer and closer to the point of tangency, so that introduced that concept of a limit. And then we then saw that we could use derivatives to find the limits. Essentially, that's what we've done here, right? If we would have chosen values of x getting closer and closer to positive 2, right? In part A, we went from 2 to 2.3, and we got 4.3 kilograms per minute. If we would have used 2.2 instead, we got an answer closer to 4. And then if we would have used 2.1, we would have got an answer even closer to 4. Again, those limits will be approaching the instantaneous rate of change, which is 4. Right? The closer that first number, the 2.3, gets to 2, the closer the average density will get to positive 4. Right? Number 5, the population of a culture of bacteria after T hours is defined by that equation. Determine the average rate of growth between 2 and 6 hours. So again, we're using that slope formula. It'll be T at 6 minus T at 2 all over 6 minus 2. So T at 6 minus T at 2. Again, we'll use our calculator here. And so that first value on top would be 2132, and I should also write the denominator, which 6 minus 2 is 4. So again, that first number was 2132 minus t at 2. Which is 948. So on top, we're going to have the 2132 minus the 948, which is 1184 over 4. 296. And if we look at this, we're talking about the number of bacteria, excuse me, after T hours. So this will be 296 bacteria per hour. That's the average growth between 2 and 6 hours. If we wanted to find the rate of growth after 5 hours, that's another way of asking for the instantaneous rate of change. So again, we would have to use the derivative. So at 5 hours, we would have to go n prime t. The derivative of n with respect to t, which would be 200 plus 24t. And so now n prime at 5 hours we'll get 200 plus 24 times 5, which is 320 bacteria per hour. And if you look at this, most of the time when we did these types of questions, we got closer and closer to that first value, which in this case would be 2. But you don't have to. Right? You can find the instantaneous rate of change at any time. It can be a number outside the average that we did above. But we would have seen, if we would have used a number closer to 2, we would have got an answer closer to 296. That's normally what we've seen, but it's not always the way that it'll be working. Okay, so we'll do some more rates of change tomorrow. This assignment you are handing in. Okay, so this assignment you are handing in. I believe that most of the formulas are given to you, or we've already seen those types of questions already. But if not, it wouldn't be hard to find them. Or you could ask. Okay?